Okay, so in this video we cover 1.8 autonomous differential equation. So in this section we will identify features of solution curves from autonomous differential equations, sketch and interpret phase diagrams, and solve autonomous differential equations including those involving the logistic growth. First off, what is an autonomous differential equation? Well, an autonomous differential equation is a differential equation in which where the derivative of solutions depend only on the dependent variable, as opposed to many other differential equations we have solved before, which typically are functions of x and y, or sometimes t and y, because oftentimes the independent variable on a differential equation it's referred to time for certain applications. Now, in this kind of equation, autonomous differential equations, we do not have the independent variable in the derivatives of the solutions. Well, so let's have a look at one example of an autonomous differential equation. So let's consider the equation dy dx equals to 1 plus y times 1 minus y, along with its slope field. Of course, I'm going to show you rather a GeoGebra picture so we can have a better overview of this. Okay, so number one, what do we observe around y equals to 1 and y equals to negative 1? Well, so number one, let me show you something here. Well, so at y equals to 1, here we seem to have a horizontal line and another horizontal line here. Oh, didn't come out perfect. Okay, so what does that mean? So when it comes to autonomous differential equations, the slope field, which is actually the derivatives of the solutions, of course we're going to have many equations many functions that at a given point we will have some slope. Now, one thing to notice about these differential equations, their solutions, all of them graphed in Cartesian plane, they seem to have some asymptotic behavior, because look at this horizontal line, look at this other horizontal line. You can think of it as an asymptote, where in some cases, for like at y equals to 1, we have functions increasing, and for really large values of x, that is, if we find the limit as x, or the input t depending on the variable, is infinity, well, so for large values, the largest y value we're going to get is going to be this value of the asymptote. Also, for functions from the top of the of this line y equals to 1, we have in this case decreasing functions with slopes that are actually kind of converge to this asymptote. All right, now what about at y equals to negative 1? So in this case we have something slightly different. So while for y equals to 1 we have all these functions kind of approaching to that y value, getting close to that y value of y equals to 1. At y, on the other hand, equals to negative 1, we seem to have these functions going away from the value of y equals to 1. So in this case, well, that actually tells us about the stability of the solutions to a differential equation. While at y equals to 1, all these functions right here seem to get close to y equals to 1, seem to settle down to y equals to 1. On the other hand, like at y equals to negative 1, we seem to have the solutions going away from that asymptotic. So we can think of y equals 1 as a point of convergence of the solutions, while y equals to negative 1 as a point of divergence of those solutions. Let's have a look at the slope field for this. Okay, so I have a slope field for the differential equation on the notes. Okay, and well, notice how for different values of x, okay, for different points, well, and here I'm just choosing points between y equals negative 1 and 1. See how all solutions for really large values of x will converge or will settle down to y equals to 1. If I choose another point right here above the horizontal line y equals to 1, see how all these curves also kind of diverge to y equals to 1. All right, now let me choose a point below below what it seems the horizontal asymptote here, so here, notice how all these curves for different points right here are actually going away from the horizontal line y equals to 1. And from the top, in this middle region right here, they're also going away from -1. However, they're getting close to y equals to 1. And again, talking about the stability of the solutions, well, so for solutions that asymptotically get to some same y value, well, we have stable solutions. However, for points where we check both sides of the y value, both endpoints rather, yes, both sides actually. But in this case, the solutions check how they actually go away from y equals to 1. Of course, we will classify these points based on their stability when we complete our first example. Okay, let's go back to the notes and see what this is about. All right, well, so for what do we observe about around y equals to 1 and y equals to -1? So number one, because this is a slope field, okay, all these lines represent the slope. Horizontal lines represent a slope equal to 0. But again, derivative means slope, that is dy dx, dy dx, yes, equals to 0, which is the slope, right? And what happens this happens at y equals to -1 and at y equals to 1. All right, and what do we have? This sort of horizontal asymptotes. Okay, now what do we notice about the slope field as we keep the y value constant, but we change the x value? Let's go back to the GeoGebra file here. Well, so I'm going to consider many different solutions where notice the y value, I'm keeping it the same. However, the y value, the x value is changing. Notice how for a given particular y value, for a given particular x value, the y value remains the same. So the slope is exactly the same right here, okay, because the slope, and that's because the autonomous equation right here, that's only an equation that depends on y, it doesn't depend on x. Okay, so what do we notice? No changes in the slopes as x changes since in this case slopes depend or only depend on y. All right. Okay, so well, let's talk about the stability of these solutions. Well, so let's have a look at this definition. So equilibrium solutions. The equilibrium solutions are the values of y that make the derivative equal to 0. Well, those are going to be also our critical points, which are the points on the y-axis that correspond to an equilibrium solution. Well, let's see. Stable critical point, that's one where a small perturbation in y does not lead to substantially different solutions as t grows. we say the equilibrium solution is asymptotically stable. All right, so that's the case where um, where we get exactly to the same value. Like here in this case, we are what do we have? We are approaching, or we are asymptotically getting to the same y value. And look at all the perturbations I'm doing to the solution. So I'm modifying by actually getting many different initial conditions, yet the behavior of the solution to the function of the solution to the differential equation has an asymptotic behavior that leads to y equals 1. Same here. Well, and in this case, we are approaching the same y value from the top and from the bottom. So that's why y equals to 1 would be a stable, um, a stable, a stable critical point. All right. Well, what about unstable critical points? Let's go back to the notes. One where small perturbations in y do lead to substantially different solutions as t grows. Well, so in this case, if I consider the case where below y equals to -1, see the behavior, see the slopes. They even just a slight perturbation. See how the slopes get actually uh, get very steep, and actually for really large values of t or x, depending on the independent variable, see how this go to negative infinity, and here on a point above this one, well, this is going away from the horizontal line that represents the equilibrium solution. So, and you can see from the slope field here, you can see how the slopes are actually going away from the horizontal line. As mentioned before, we have some sort of a divergence away from the horizontal asymptote, while at y equals to 1, we have some convergence for those functions. All right. Okay, so let's go back to the notes and answer the questions here. Okay, so for example number 2, they're asking us to draw the phase diagram for example number 1. So what are we going to do? Okay, we're going to do a number line. Okay, so number line at with the y values. So we're going to plot the y values that describe um, the the equilibrium solutions. Well, so what are we going to do? Well, let me rewrite the differential equation again. That's dy dx equals to 1 plus y, 1 minus y. Okay, so the problem we are about to solve here is that in which that is very similar to what you did back in calculus 1 when you plotted the critical values to check the increasing decreasing behavior to determine whether you have a maximum or a minimum. We're going to do something similar. However, this is to check the stability of the solutions to a differential equation. Well, so for this we're going to need some test values. So a test value between negative infinity and -1, I like -2. Between -1 and 1, the easiest is 0. And between what do we have? 1 and infinity, I like 2. All right. Okay, so these are going to be our test values. What are we going to do with these test values? Well, substitute them into the differential equation to have a look at the values, or rather the signs of the slopes. Well, so what do we have? 1 plus y, that is 1 plus -2. 1 minus -2. Well, this is actually negative and then positive. Well, negative times a positive, what is that? It's negative. Well, we will represent the negative behavior with an arrow pointing to the left. All right. Now for 0, well, 1 plus 0 times 1 minus 0, that is positive times a positive, which is positive. We're going to represent positive with an arrow pointing towards the right. Let's repeat the process for 2. 1 plus 2 times 1 minus 2. 1 plus 2, which is positive, 1 minus 2, which is negative. This is going to be negative, which is represented by an arrow pointing to the left. Okay, so let's talk about the stability here. So this means we have our solutions unstable for y equals to -1 and stable for y equals to +1. Well, just to compare this with the phase diagram, we did not the phase diagram, the slope field. This is what we did here. It's called a phase diagram. The other graphs are called slope fields. So see what's going on at around -1. See the two arrows going away from that equilibrium solution or critical point. Okay, we saw it on the graph right here. So at y equals to -1, see the slopes increases from above, however decreases from below. So we can see the solutions stepping away from that asymptotic. Okay, what about at y equals 1? See the slopes, how they both converge to y equals to 1. Well, here we can see the two arrows converging, two arrows diverging, if you will. All right, well, let's have a look at another example. Well, consider the differential equation y dy dt equals to 3y to the fourth minus 11y cubed minus 4y squared. Well, so we need to factor this polynomial so we can get the equilibrium solutions. Well, so actually what I'm going to do here, I'm going to write the polynomial 3y to the fourth minus 11y cubed minus 4y squared equal to 0. Factor out y squared, 3y squared minus 11y minus 4, and set that equal to 0. So now we need to factor the trinomial inside of the parentheses. There are many methods to factor quadratic polynomials with a coefficient other than 1. I'm just going to give you the solution. Just stick with your favorite method to factor it. So that's going to be 3y plus 1 times y minus 4. Let that be equal to 0. Using the zero product property, this tells us y equals to 0, this tells us y equals to -1/3, and this tells us y equals to -4. All right? Okay, so actually I would like to rewrite the factor polynomial over here because we're going to use it to test later. Okay, well, so this is the same as saying y squared times 3y plus 1 times y minus 4. Okay, so find the critical points and sketch the phase diagram. That's part B of the problem, and we're going to repeat the number line we did like we did in the previous example. So let's see. So what do we have? Number line, critical values, -1/3, 0, and 4. Okay, so in this case we have 4 regions to test. All right, well, between -infinity and -1/3, I like the number, I'm going to do -2 again. Between what's it called, between -1/3 and 0, there's no nice integer to test. However, I will have to use 0.1. All right, okay, so between 0 and 4, I'm going to use the number 1, and between 4 and infinity, I'm just going to use the number 5. All right, well, so for the differential equation, so -2 quantity squared is positive, always positive, and then 3 times -2, which is -6. Let me do the whole thing. So -2 squared times 3 times -2 plus 1 times -2 minus 4. Okay, so this is positive. 3 times -2, which is -6, plus 1, that's negative, and then -2 minus 4 is negative. So multiplying the signs, we get positive times a negative, which is negative, times a negative equals to positive. So we will represent this with an arrow pointing to the right. All right, What about, okay, let's repeat the process for the next test value. All right, so number one, negative 0.1 squared times 3 times negative 0.1 plus 1 times negative 0.1 plus 1. Okay, so this is always positive, and then negative 0.1 times 3, that's negative 0.3 plus 1 is going to be 0.7, which is positive. What else? 1 plus negative 0.1, is that also positive? So, well, actually, let me double check the work here. Okay, silly mistake here. This should have been a 4, so that's actually and minus 4, not plus 1. I don't know where I got the plus 1 from, so this is negative. So negative times a negative is positive times a negative, it's going to be negative. So that gets represented with an arrow pointing towards the left. Now the test value at y equals to 1. Okay, let's repeat. So 1 squared times 3 times 1 plus 1 times 1 minus 4. Okay, so this is positive, this is also positive, and this is negative. So we have another negative here. Okay, let's represent that negative with an arrow pointing to the left. All right. Okay, so for the next test value, what about 5? Okay, so this is 5 squared times 3 times 5 plus 1, 5 minus 4. Okay, what do we have? Positive times another positive times another positive. Everything is positive here. Okay, so we have this as an arrow with an arrow pointing towards the right. All right, so that's the phase diagram. Okay, so that's the phase diagram of the differential equation. We're going to look at slope field shortly so we can get an idea and actually verify our work. So now for part C, they're asking us to find, or rather to classify our critical points as stable, unstable, or as semi-stable. We're going to talk about that in a second. Okay, so at y equals negative 3, y equals to 0, and y equals to 4. So notice the behavior around negative 1/3. So the two arrows are actually getting to that same y value at negative 1/3. That's why we have a stable point, right? What about at y equals to 4? At y equals to 4, we have the two arrows going away from its value, so we have this unstable. Okay. However, at y equals to 0, there's something interesting going on, because while it's from the right of it, we have the solutions converging to 0. From the left of it, they're not converging to 0. Actually, they're converging to the previous critical value. So we have what we call a semi-stable solution, or we can call it semi-unstable. Either way, semi-stable, it's fine. All right. Well, so let's have a look at the last part of the problem. So for each initial condition, determine the long-term behavior of some function y of t, that is the limit of the function as t approaches infinity, containing the initial condition y of 0 equals to 5. So this means we need to let's have a look at the number 5 right here and put it on the number line. Well, actually, okay, let me use a different color for this. For y equals to 5, okay, at y equals to 5, you can think of the number 5 right here. It's going to do whatever the arrow is doing, and see, where is 5 going to? Well, it's just going to positive infinity. So this green arrow is pulling that 5 towards positive infinity. So in this case, we can simply say y of t approaches infinity. All right. And well, we're gonna have a look at that in the slope field shortly. What about y of 0 equals to -2? So let's look where we have the number -2. Actually, we have it right here. All right. So now the number 2 is going to step on the arrow and it's gonna go on a trip. So where is this number 2 going to be pulled to? So it's going to approach to -1/3. So it's going to take a right and get to -1/3. All right. So in this case, y of t equals to -1/3. Okay, let me make something up. So a couple more examples. Number 3, say I would like to say y of 0 equals to 1. Okay, so where is 1 actually? 1 it's actually here. So this number 1 is gonna step on the arrow, on the green arrow, and go for a ride. Where is it gonna get to? It's going to get to y equals to 0. So y of t will approach to y equals to 1. All right, so let's have a look at the phase diagram for this differential equation. Okay, so here we have the phase diagram for the differential equation we were working on the example. So notice how we have some sort of a horizontal asymptote at y equals to 0, at y equals sort of negative. Okay, the -1/3, it's somewhere here. It's kind of hard to catch this asymptote here. However, we can see the behavior. Okay, and the one at y equals to 4. So but at y equals to 4, that's going to be a harder one to see because of how steep the slopes are. However, we can see the direction of the slope, like a positive slope here and then a negative slope here. Okay, let's verify our work for the previous example. Okay, so at -1/3 we have positive slope and then negative slope. That's a stable critical point or critical value. Okay, let's verify that. Okay, so at y equals to -1/3. Okay, so somewhere here. Okay, see how the slopes behave. They go down above it and they go up below, so they converge to this horizontal asymptote. I mean, again, it's kind of hard to. Okay, here it is. That's what it is. Okay, here we have it. Finally, that's a horizontal, sort of. Okay, sort of. However, again, they both converge. Okay, so what about around 0? Okay, let's go to 0. So we should have negative slopes below 0 and also negative slopes above 0. Let's see. Okay, so at around 1, y equals to 1. Okay, well, that's another hard one to get. So at y equals to 1. Oh wait, no, I said y equals to 0, not y equals 1. Y equals 0. See how we have negative slopes, also negative slopes, so we have a semi-stable critical point. And finally, the one we want to verify, it's the unstable point at y equals to 4, where we have both both slopes going away from the equilibrium solution. Well, so at y equals to 4, okay, see how negative slope, positive slope, very steep slopes. However, we can see how the solution is, or the critical point, it's actually an unstable one. All right.